Welcome to a new set of videos on matrices for further mathematics. This is going to be an introductory video which we're going to look at what are matrices and what are their benefits. And I've got three examples we're going to use. Quite often and really useful in computer science, where you'll see them described as arrays. And if you think about it, it's like we've seen spreadsheets where you've got rows and columns, and you're using lots and lots of data, and you need to play with it, and you need to do operations on it, play around with it, and that's what we're going to use matrices for. So this one, I'm just going to show you some uses. Well, the first example, the one that we usually introduce matrices with, is solving simultaneous equations. So here I've got two simultaneous equations, 3x plus 2y equals 9 and 4x plus 5y equals 5. Well, if you think about that, that's really what we've got here is two unknowns, x and y. Well, effectively we've got the coordinates of a point, haven't we? And if we wrote them as a column vector, we've got xy, so that's xy. And then we've got all these multipliers, the 3, the 2, the 4 and the 5. And we can try and separate those out into what we call a matrix. Here it is, 3, 2, 4, 5. You can see they're configured in the same way. But we need a rule because effectively we're multiplying these two together. We don't tend to put the dot there, but effectively we're doing a multiplication. And we need a rule to explain what we're doing with those two sets of numbers. So to reproduce what we've got on this left-hand side here, we need to read that as being, if we take this row here, 3, 2, and we multiply those two numbers by xy, we get 3x and we get 2y, and then we add them together, so we get 3x plus 2y. And that's, we need to have that fundamental idea about how to multiply matrices and vectors together, and we always do the same thing. So for the lower value here, we're going to get the 4 and the 5, we're going to multiply those by the x and the y, and we're going to add them together, so we get 4x plus 5y. That's what that fundamental multiplication operation means in matrices. So once we know that, we can split these out, can't we? We can now split out the matrices, so the coefficients into the matrix, and then we've got our column vector of xy there. So if we know that this is the matrix, what we would normally do here, if I had an equation, I've got my matrix times column vector x equals p. If I want to solve that, we'd just usually divide by m, wouldn't we? So x equals p over m. We can't really do that in matrices, but we've got the opposite of multiplying is, rather than division, it's finding the inverse. We multiply by the inverse. So we've got an algorithm for that. We call an inverse, we've got an m minus 1, little minus 1 there tells us an inverse. And we've got an algorithm which we'll go into in future work, and that would give us an inverse matrix. And as a result, we know, but we can reverse this equation here, and the next step would be therefore x is m inverse times p, which was our constants vector. So there we have xy is going to equal this matrix inverse, which we did above, times by p, and using the same rule, that times that, and that one, this row times those numbers as well, we would end up with answer calculation of 5 minus 3, which is the column vector for this point here, 5 minus 3, isn't it? Now you might say that was an enormous amount of work just to solve two simultaneous equations, but the same method applies to 3 simultaneous equations or 4 simultaneous equations. So if I rewrite it into a vector as our matrix format, then I've got my matrix of all the coefficients there, the multipliers. I can use an algorithm to find my inverse, and therefore to find my x values, I multiply my inverse by the constants we had on the right hand side. So there's my m minus 1, multiplied by the constants, gives me this a vector here, 1, 2, 3. So that's telling me that my solution is x equals 1, y equals 2, z equals 3, isn't it? It's the point 1, 2, 3 in 3 dimensions. So there we go. We could do that for 100 dimensions or 100 unknowns using this approach. Next thing it's really useful for in mathematics is transformations. So if I take this matrix there, and I start with the 0.21, I multiplied it through that 2,1. Out of the calculation would come 6,1. Well, what's that look like for my P dash? Well, actually, it's a stretch, isn't it? Times scale factor 3. And that's the scale factor 3 there in the X column and row. So what's this 1 here? You wonder. Well, that's actually saying to us that in the Y direction nothing changed, so the scale factor was 1. So this matrix will take any point and transform it by the stretch of times 3 in the X direction. What's this matrix here do? Well, if this one does reflections in the XY line. So if I start with the 0.21 here and I multiply it by that matrix there, the answer that comes out is 1, 2. So it's that point there. So it gives us the reflection point. Yep, object and image. And that's true of any XY. If I put XY in, I get YX coming out the other side for the multiplication. And what about this last one? Well, this is a rotation matrix. Tells us what's going to happen to points. So if I started with a point 1, 0, multiply it by this matrix, I end up P going to P dash. I end up at the point cos theta sine theta. Well, that's where I want to be, isn't it? If I've been rotated by theta. And if I started off with the point 0, 1, yeah, I'd put these in vector form, of course, like 0, 1. Then I would end up at the point minus sine theta cos theta. So that's gone from there to there, isn't it? Which is what we'd expect. And this is true using this matrix. We'll do it for any x and y value. We'll rotate it round. So that's really useful. And next one is quite often used by companies where they're capturing lots of data. So if I'm running a pizza delivery company and I've got 4 types of pizza, Hawaiian, seafood, meat feast and vegetarian, I've got 3 sizes, regular, large and family. Each evening I might work out how much I've sold, what my orders were, and put it into a matrix. So here this 2 means that I sold 2 Hawaiian regulars, or this 3 tells me that I sold 3 vegetarian family pizzas. And if I wanted to know how much that lot cost me, and I knew that a regular cost me £2.50 to make, and a large cost me £3.50, and a family cost me £4, what would my total cost be? Well, there's my matrix. First thing I want to know is how many of each size I've sold. Well, I can do that by multiplying this by this vector here, 1, 1, 1, 1. So using the rules of matrices, I multiply those 4 numbers by those 4 numbers, and that would tell me that I've got 2 plus 3 plus 1, I sold 6 regulars. And for the next one, if I did 5, 7, 8, 4 by the 1, 1, 1, 1, it would tell me I've got 12, 20, 24 large pizzas I'd sold. And then I multiply the 6, 4, 3, 3 by the 1, 1, 1, 1. I get 6, 4, 10. I get 16 family pizzas. And if I now multiply this horizontal sort of line vector with that column vector there using matrix multiplication, so 2.5 times 6, 3.5 times 24, and 4 times 16, I'm going to end up with 163, which is £163 is what it cost me to make these pizzas. So again, that would be quite a long thing to do, or lots of bits of paper, but we can describe that using matrices just like that. So there we have it. We can use matrices for solving equations, doing transformations, and doing heavy calculations in computers with large amounts of data. It's got its own sets of laws, matrices, addition and subtraction. Basic multiplication look a bit like they do in just ordinary numbers, operations of 2 times 3, or sorry, 2 plus 3, things like that. But inverse multiplication, there's no such thing really as division, so we have to have an inverse multiplication instead. And so we got that process which we'll look at, and we've got commutativity. Doesn't work the same way in multiplication. 3 times 2 equals 2 times 3 in ordinary multiplication, doesn't it? But matrix M times matrix N does not equal matrix N times matrix M. And we also have to look at shapes, because we have to make sure that our matrices are the same shapes. So there we have it, a quick introduction to why we have matrices.